We're looking at the conservation of mass, and we're going to investigate some reactions, and the first one will be the combustion of ethanol, and we're going to look at it on the atomic or the molecular scale. So first of all, let's look at some molecules here. The first one is going to be ethanol, and here we've got a ball and stick model, and you've got the standard atom colours for carbon, hydrogen and oxygen, and a representation of part of its shape. So the reactants, when we're burning ethanol in air, are going to be ethanol, and it's the oxygen in the air that's going to react. The ethanol is a liquid at room temperature as you start the reaction, and the oxygen is a gas. Now, what are the products? If you have hydrocarbons, compounds that contain hydrogen carbon only, or alcohols which have that OH group on them, and you've got plenty of oxygen, you will produce carbon dioxide and water. This is a slide you might want to come back to look at. And so we can write the equation in words, and underneath it draw the molecules. All covalently bonded, these are all non-metallic elements that are here. And what we're doing is an audit of how many atoms you've got in the reactants, how many atoms you've got in the molecules in the products. So to start off with, the black atoms, they're the carbons. You've got 2 on the reactant left side, 1 on the product right side, 3 red oxygen atoms on the left, and 3 red oxygens on the right. On the left, you've got 6 white hydrogen atoms, and on the left, you've got 2 hydrogen atoms in the product water. And so, just looking at the balancing, the carbon atoms aren't balanced, the oxygen atoms are, and I've put at the moment because sometimes when you rebalance the others, it interferes with what was already balanced, but let that happen. And the hydrogen isn't balanced. And as a tip for balancing, don't start off to balance the atom if it appears in more than one element. It just makes it a little bit harder to do. And so what we're going to do, we're going to look at the carbon atoms. So we want 2 carbon atoms on the products. And I'm not just going to put in carbon, like charcoal. The only place carbon appears in the products is in the carbon dioxide molecule. And so I need a second carbon dioxide molecule in order to get a second carbon atom. Now, if I do that, I've got 2 carbon atoms on either side, and I've now got 7 oxygens on the products and only 3 on the reactants. So I'm then going to balance the hydrogens. I want 6 on either side, and there are 6 in the C2H5OH ethanol molecule. There are only 2 in a single water molecule, so I need 3 water molecules. So that's what I've drawn there to get my 6 hydrogens. It also brings 3 oxygens. So when I recheck, my carbons are balanced, 2 each side. My hydrogens are balanced now, 6 each side, but my oxygens aren't. 3 on the left-hand reactant side, but I've got 7 on the product side. So I need to balance those. I want 7 on the reactant side. I've already got 1 in ethanol, don't forget that one. And so I need 6 more, which is going to be 3 diatomic oxygen molecules. And those numbers, how many of each type of molecule you've got, become the balancing coefficients in the chemical equation with the formulas above. So 1 ethanol molecule with 3 oxygen molecules gives me 2 carbon dioxide molecules and 3 water molecules. Now, what we've actually got now is the same number of each type of atom on both sides of the equation. Chemistry is magical, but not magic. You can't make atoms that weren't there in a chemical equation. But what we're saying now in terms of the law of conservation of mass, because you've got the same number of each type of atoms on either side of the equation, your mass has been conserved during the reaction. And so that is your law of conservation of mass. I'm going to look at an application here with rocket fuel, and in the V2 rocket it was fueled by alcohol and liquid oxygen. The alcohol was actually a mixture of 75% ethanol, 25% water, and so the reaction, the chemical equation there, is exactly the same. And whether it is burning in space and you have to take its own rocket, own oxidizer, and this was the first ballistic one to go high enough to go out of the Earth's atmosphere, taking liquid oxygen with it, you have the same number of reactant atoms as product atoms in the fully balanced equation. And so if we're looking at the equation, got the reactants, and then we've got the products, which are pretty similar there as well. Now you're going to do a little bit of understanding, and so part one is a chemical called ethyne, and it's made up of hydrogen and carbon only, burning with an oxidizer oxygen. But ethyne's its systematic name, it's known as acetylene, the gas in oxyacetylene. When welding, predict what the products are. Oxygen with the molecule of ethyne. And put in those products and draw the actual molecules, ball and stick models of them, to balance the equation and then finish the equation above. I'm going to ask you to do the same for propane. And this is barbecue fuel, the gas barbecue fuel. Again, it's a hydrocarbon, C3H8. And what are the products? You can go back to that earlier slide that I reinforced that you might be needing later. But the oxygen is going to add onto the C and the H, but it's going to split up the propane molecule. And here's the ball and stick model for propane, and you can finish the others and balance the molecule. And if we're going to look at the first liquid-fueled rocket, 1926, Robert Goddard designed and flew it. This actually used gasoline and liquid oxygen as the oxidizer and flew in Massachusetts in March 1926. And you've got the equation there, which is really quite chunky for some of the equations that we see in terms of numbers of molecules. And I'm not going to ask you to draw all of those out, but you can if you like the practice. Another of his rockets, the A series, that again used gasoline and liquid oxygen.